Okay, so what we want to do today is a quick demonstration of the one of the machine learning functions that's built into VxL 3D. It's a function called trainMLP. It's actually a set of functions. The MLP stands for multi-layer perceptron. It's a set of functions that allow you to create neural networks, artificial neural networks in Excel using your Excel data. So you have trainMLP, which does the initial training of the network, retrainMLP, which allows you to start with a set of weights that you did from a previous training, and then continue the training with those weights being seeds for the perceptrons in the next learning batch. vxExecuteMLP, which allows you to execute a trained network on new data, and then vxViewMLP, which allows you to actually view what the network looks like. And so what we want to do today is we want to just briefly go over how we would create a neural net and train it using Excel and VxL 3D. So we're going to start with some data. This is a very simple network. It's 150 samples of iris plant data. So what it is three different species of iris, and we have 4 inputs, which are here. These are just physical measurements of the plant. And this is a database that this is a set of data that you can download and play with. There's actually quite a bit of good data that you can sort of play with and build your own networks with to get a feel for this one. But for demo purposes, this is a really nice, clean database to work with to do training on. So we're going to start, and what I want to do first is just take a look at, I'm going to use the vxMLP function to take a look at what our network looks like in this particular case. So this is the vxMLP, and we're going to turn off a few things here. Okay, so this is my network, and this is just a 3D representation. This is a trained this is from a previous training cycle, and you can see basically these are my input nodes here. The white columns are the input nodes. I have 5 in this case. There are actually 4 inputs in my data, and then I've added 1 bias node to this network, which is not really necessary. It doesn't really affect the accuracy of this particular network. We'll talk about that in a second. But these are my inputs here, the white ones, the white columns. The green columns represent 1 hidden layer in this particular network, and then the gold yellow columns here represent the 3 outputs, and those are my 3 species of iris. So what I'm going to do here, and you can see these are the connections that are in between each one, so you can see each of the input nodes connects to each of the output nodes. So you can see this node here connects to all 4, and then this one connects to all 4, and so on. And then each of the hidden layers, each of those nodes connects to each of the output nodes. And the colors of these connections actually tell me the weights of those connections. So the blue lines represent low weight values, the red lines represent high weight values, and the colors in between, the purple and the indigo and the violet, those are intermediate values. So the closer they are to blue, the lower they are, and as they go red, then the higher the values, the weight values are. So we'll close that here for a second. And we'll come over here and we will look at our function, our train function. So this is my array. So I've already actually done a training. So we're just going to retrain over this existing data. And you can see the function here is called trainMLP. And these parameters that you see here are all of these right here along this top bar. The first thing we have to do is we have to get a network size. So there's actually a function that's called getMLP return size. And what that does is it tells me the size. Once I've configured everything, it tells me the size of the network so that I can then define an array of columns here. I can highlight these. This kind of works like a matrix function where I highlight a range, and then I enter in my function, and then I hit the Control-Shift-Enter to apply that then to that range of cells. So I need to know what size my range is so I can get all of my return data. And that's what this function here, which is get MLP return size, does. And it tells me, in this case, 43, so I know, okay, I need to highlight 43 cells right there, and then I can run my function. So each of these are represented here across the top. So the first one here, learning cycles. This is basically the number of times that the network is going to run through the data that I give it to train the network. So when we first create the network, all of the weights are random values. They're seeded with random values. So initially, the network is simply guessing at the output based on the input. So we give it an input, and it just guesses what the output is. And so obviously the accuracy is going to be very, very low. And so we go through that, and we take the results, and we feed it back through the network, and we tweak the weights, and we just continue that process, whereas it's an iterative process. So we're simply going through a number of iterations where we're feeding in the inputs, we're looking at the outputs, we're tweaking the weights, and we just keep doing this. And over successive iterations, successive cycles, the network is going to learn and will self-optimize, and then will hopefully give us a network that we can then use to make predictions when we start giving it new data. So the idea is to take existing samples and use that to train the network, so that we can then make that network available in our worksheets, so that we can plug in new data and have the network make predictions as far as what the outcome should be based on the new inputs that we're giving it. So the initial learning cycle is just the number of times we're going to go through that initial cycle. And usually what will happen is you go through a set of batches. So we'll do, in this case, we've set up 32,000 learning cycles. So we're going to go through 32,000 times. And I know from experience that with this particular data set, that's going to give me a very high accuracy, because this is a very well-behaved data set. You may have to go through far more training sessions and more batches in order to get, depending on the complexity of your data, the number of inputs. And again, the input size, I mean, this could be considerably larger. Here I just have 4 inputs. I could have dozens of inputs. I could have hundreds of inputs. And similarly with my outputs, I could have far more than 3. So that's why I said this is a relatively simple database. So the next thing I have are my hidden layers and my hidden nodes. So if we go back here and look again at our network that we've configured, we can see that there is one hidden layer, which is this one right here. The more complex the data that we're building the network on, potentially the more hidden layers we may have. And it's very much dependent upon the complexity and the relationship of the attributes, our input attributes versus our output results. So it's difficult to say. It doesn't necessarily go with just if I have more inputs or more data that I necessarily going to have more hidden layers. I may have more nodes in my hidden layer, depending on the number of inputs that I have and the number of outputs that I have, but I may or may not have more layers in my data. The depth of my network may or may not increase, and part of that is going to be based not so much on the size of the input data, but how well the attributes that I'm using correlate to the output. So for a lot of projects, 1 or maybe 2 hidden layers will be sufficient, but they may have considerably more nodes in the hidden layer, but that's what this layer is in between. Now, if when you're setting this up and you say, well, we'll start with 1 hidden layer, but I'm not sure how many nodes I want to have, you can set that to 0, and then the software will automatically choose a starting point for your hidden nodes. And it's going to look at your inputs, it's going to look at your outputs, and it's going to make a best guess at what it thinks would be an appropriate number of hidden nodes to have in your hidden layer or your multiple hidden layers. So you can set that to 0. In this case, we simply set it to 4 because, again, I know that that's going to work just fine. Here I have my learning rate. I've set this learning rate lower than what it needs to be. This is the learning rate is basically how much the weights change from iteration to iteration. So as the software is going through, and again, it's going to start with a set of random seeds, and it's going to begin making guesses, and it's going to look at the accuracy of those guesses, and it's going to tweak the weights. This is going to constrain how much those weights change. In the early learning of any network, we can assume that we're going to need to have some fairly large changes because we're starting with random values. So the likelihood that we're going to randomly choose a weight that's going to be close to an optimum weight for any given node is pretty low. So we can assume that a relatively high value for my learning rate, say 0.01, in my initial training stages would be appropriate. And then as the network trains, I'm going to want to lower that value. Because as I begin to get close to an optimum answer, if that value is too high, I may actually overshoot my optimum answer, and I may see my accuracy begin to get better and better and better, and my confidence begin to get better and better and better, and then I'm going to see my accuracy starting to get worse and worse and worse because I've actually overshot my optimum values because my learning rate is too high. So the software will allow you to set it. Actually sets an initial learning rate, and if you have your monitor learning turned on, which is another option, you then have the ability of the software actually monitor that and will tweak that learning rate, so you can start with a relatively high number, and then you can let it begin to move to a smaller and smaller number, which sort of slows down the cycle-to-cycle change in the network, assuming that you're getting close to an optimum value and you want to sort of zero in on that value. In this case, I've set it to a relatively low rate to begin with because this particular data set trains extremely fast and it wouldn't be much of a demo. So what I've done is I've actually set it to a low rate just so it will move relatively slowly through the training process so you can get a feel for how it works. But you would usually, on a much larger set, you would set this high, and then you would let the software gradually reduce that as it begins to zero in. Your next option here is your activation function. Again, we'll pop back here real quick to our network example. Each one of these nodes, each one of these perceptrons has a number of inputs and a number of outputs. And so the inputs, once the inputs reach a certain threshold, then the node outputs to the next layer in the network. So there has to be some type of threshold trigger. And there are different ways, different models of defining those network triggers in how the node actually decides to output based on the inputs that are coming in. And so we actually have 12. So the simplest is just a linear threshold, which is a very simple linear function. A more common function, and one that's very commonly used for a lot of neural nets, is a sigmoid, which is the default in this case, which is more, well, it's a sigmoid function, so it's more of an S-shaped curve. And that's what we use here for the default. You can play with some of these others. There are some, depending on the data that you're looking at, that you're trying to train on, and the type of network that you're setting up, different activation functions might make sense. There's more information. I'm not going to get into all of these in this demo. It would take far too long, but in the help documentation that comes with VxEl would be a description of these, and when some of these might be, some of these activation functions might be more appropriate in certain cases than others, and so you can kind of get a gauge for what you might want to choose. There is a certain amount of trial and error in setting up any network, so although we do have automatic optimization functions that are built into the software, and we're continuing to improve upon those, it's not as simple as just dumping in a bunch of data and letting the software figure it all out. You do have to make some decisions initially, and sometimes it requires a little bit of trial and error run a set of batches, see how it trains, change a few things like your activation functions, your hidden layers, your hidden node size, and then run another batch and sort of get a feel for what's going to be the best configuration of a network. And then once you've actually configured that network, then you can get extremely good results. But there is a certain amount of trial and error, and Excel does make that very nice to be able to play with different settings. So this just allows you to sort of set some of these things. Auto normalize. All of your data that's on your input has to be numeric values. We currently don't support text-based input, so it would have to be converted to numeric values. But obviously the numeric values can be pretty much any range that Excel supports. For training purposes, when you're setting up the network, it usually makes sense to normalize all of your inputs or standardize all of your inputs. You can do that yourself, because there are different ways that you might want to do that, and so you can turn the auto normalize off. You can just feed the data as is to the network. It doesn't really care, but it may not train optimally depending on how the kind of ranges that you have on your different attributes. Or you can turn the auto normalize on, and basically what this does is it just applies an auto normalize. In this case, it standardizes the data to a mean of 0 with a standard deviation of 1 for all of your inputs, and it records that data in the neural net. So when you go then to apply the neural net, you don't have to remember, oh, did I auto normalize that or not? The vxExecuteMLP will look at the neural net and say, okay, this was auto normalized, so it will be able to automatically apply those same normalization values to any new data that you feed it. And the same thing with the retrain, it will say, okay, this is auto normalized. So if you begin adding additional samples to continue to train your network with, as new data comes in, it will know how you configure this, and it will stay with that same configuration. So if you select auto normalize now in your initial training, it will retain that as it goes forward. The bias node, I mentioned that I had a bias node set true for this last network. That's why I have 5 inputs instead of 4. It's not really necessary for this particular data set. Larger data sets, more complex data sets, it might actually help to improve accuracy. Again, there's a lot of reasons why you would use that. It's discussed. I'm not going to get into it now, but it's discussed in the help documentation is why you might opt to add a bias node. And again, this is something that you need a little trial and error to determine if it gives you how it affects your results. There's a very, very small performance hit with large networks, with large data sets, if you enable the bias node. So that's why you can turn it on or off. But it's when it's effective, it's a negligible performance hit. The next one we have randomized samples. This is actually an important one. Depending on the data that you get, normally what would happen if this is set false is that as you go through your learning cycles, it's simply going to start with, in this case, it's going to start with the first row of data, and it's going to proceed to the last one. It's just going to keep going through the cycle, however you pass it from Excel. If you set randomized samples true, it's going to shuffle this data. So each time it goes through a learning cycle, it will reshuffle the data in a different random order and apply that to the learning. So it's going to effectively, every possible way that you could shuffle this data will be shuffled and fed through the learning cycles, and it will just do this in a random order. That tends to improve the effective accuracy of the network as you begin to add new data. So once you've trained the network, you may not see this, the randomized samples in your initial training, but when you begin then feeding it new data into the network, randomizing the samples will tend to give you more accurate results with new data as you begin feeding it in. The next option we have monitor learning. This just allows you to, as I said, tells the software to periodically take a subset of your training data and use that to test the result and then give you an accuracy score. So what you're doing is you're effectively taking this, and this could either be a subset of your data or it could be a separate set of data. If it's a subset, then it simply randomly pulls a subset of samples, tests those, and then reports that and uses that to auto-optimize, whether it's adjusting the learning rate or other factors. It does have a small performance hit when you do that. Both the randomized samples and the monitor learning do take a performance hit as you're going through, particularly with very large data sets. So sometimes you may opt not to run, for whatever reason you may opt to not use either one, which you get maximum training performance. If you're running in relatively small batches initially, if you're trying to configure, figure out the best configuration for your network, how many nodes, how many layers, you may want to simply turn that off and run small batches and then see your results. And then once you finally decide, okay, this is the an optimum configuration for my network, and you're going to go through and run a large number of learning cycles, and you can then turn on the monitor learning. You can allow the software to apply some of its auto optimization functions, like adjusting the learning rate. And again, it will feed that data back to you, so you can actually see as it's training. You can see where it might plateau. You can see where it starts bouncing around. If your learning rate, for example, is too low, you can see where the accuracy starts bouncing around. You can see where your confidence level sort of plateaus or begins bouncing. So these are some things you can see when you have that monitor learning on. You can actually see that feedback in real time. But there is a small performance hit. And then the final option is the multi-CPU mode. And what this does is it takes advantage of multi-core processors. Most modern PCs have multiple cores, but there is a performance hit with setting up and running on multiple cores. So with a small database like this, it doesn't make any sense. You can run this very quickly with just a single core. But if you're running with a very large data set, or particularly a very large network with a lot of layers and a lot of nodes, then running it on a multiple core, enabling the multi-core mode does make sense. It can improve the overall performance of your system. However, it does really tie up your system. So it's one of those things that if you enable it, then you pretty much set it to let it run and walk away, because it will really tie up all of your cores for that period of time that it's going through the training cycles. So again, it's one of those things where you sort of have to decide if it's a very large data set. You can test it and see if employing the multi-core mode actually gives you a performance boost. And it's also going to depend somewhat on your architecture, the type of processor you're running, and the number of cores that you have. So now that we've done this, we're going to set up. I already have configured my array here. So I would run my get MLP return size, and I would effectively give it my data. I would tell it whether or not I'm setting up a BIOS node, auto-normalize my hidden layers, my hidden nodes, and basically my configuration of my network. And it would tell me, okay, I need an array of 43 cells. So I would then highlight that, and these 43 here. And then if I click on my function wizard, I can actually get a little description of what each one of these are as I go through. And this just tells me down here what it's looking for in each one of these settings. So we've already set that all up. So I'm just going to go ahead and let it run. Now the first thing it asks me is it warns me that I'm going to initialize the network and begin training. And it asks me if I really want to do that. If I had done this inadvertently, or if the auto function in Excel had started and popped this up, I might want to say, no, I've just spent 2 hours running this training and I don't want to overwrite this. I could say no, and it wouldn't overwrite. In this case, I'm going to say yes. And then the next thing it's going to do is it's going to allow me to save this. And this is an option. Up here at the top, you see this true. That's actually an auto backup mode. And so if I set the auto backup mode to true, it does two things. It pops up this file save dialog and allows me to specify, and I'm just going to overwrite one that I've already used, but it allows me to specify a file name for a CSV file that's going to store my array. Now in this case, I have 43 samples, and this is going to train very, very quickly. but I could have a very large network that could have hundreds or even thousands of weights in that and could have taken hours to train, and it's not something that I'm going to want to inadvertently overwrite. So as a fail-safe, I can save this to a CSV file. So if something happens, I have it backed up to a separate file. The other nice thing is that this will update this periodically. So if I'm going through a long training cycle, let's say I've set this for 500,000 iterations, and I'm running for several hours in a very big data set, periodically as it's running, it will back up all of my weights, all of my structure to this CSV file. So if something were to happen, I lose power, Windows crashes, some other fluke occurs, I have all of my data backed up, so I don't lose all of that time that I've done. So again, it's just a fail-safe. With a small data set like this, it's completely unnecessary, but I'm just showing it that you do have this option. So I'm going to say save, and yep, I'm going to overwrite that. I know it already exists. And so now I am in the actual dialog box, and I only have about a minute here because this is going to train very quickly. This is going through 32,000 iterations. It's doing the monitoring every 3,200 cycles, about every 10%. And it's showing me here my overall accuracy, which is climbing very quickly, and my overall confidence, and then it's showing me how this is training, or how this is trending. So you can see my confidence is increasing, and my accuracy is increasing. And this confidence sigma is just the standard deviation on my confidence, how much variation I have from sample to sample in my overall confidence. This shows me my estimated time remaining, which is about 6 seconds. It shows me my learning rate, and so, and I'm done. I do have the option in this. If you take a look at this video again, you'll see there's an option that says stop and return results. If I were running this on a very large network, and I was running a large number of iterations, and I was monitoring this, and I saw that I had sort of reached a peak point where my accuracy had plateaued and it really wasn't getting any better, it was sort of bouncing around, I could at that point click stop and return results, which would do 3 things. It would stop the training process, it would save those results one last time to my backup file if I had that turned on, and then it would return the results back to Excel. And then once I had that there, I could look at the results, I could play with them, and then I could restart my training based on the weights that I had here. So I could use the vxRetrainMLP function, where I would actually select the neural net and my data, and I'd say, okay, keep training. It might be one of the situations where I might want to plug in some additional data and see if adding more samples might improve my accuracy, or using a subset of my samples might improve my accuracy. So again, it's the ability, I can stop that. I don't have that. So if I set it for 500,000 training iterations, and I see that after 50,000 I'm not really getting anywhere, after 100,000 I'm not getting anywhere, I can go ahead and stop, save those weights, make some changes to my configuration, and then restart the process with those previous weights. So in this case, if I've got my results, and I'm going to move over here, and so this shows me that based on those initial 30,000 with the configuration that I had a 94% overall accuracy with a 75% confidence in making my predictions. And this is just a graph of my predicted results. And so what's going to happen is when I do my output class, the output class in this particular data set was all text-based, so I had to convert that to a numeric output, 1, 2, or 3. And then I had to set my outputs for my samples as binary, so either 0 or 1. So I have output 1, 2, and 3, and then I have whether it's was yes or no, binary output. Then when I get my results back, they're going to look like this. So for example, here you can see 0, 1, 0. And then this was the result for that particular output was 0.09, 0.85, 0.05. So clearly it chose number 2 with very high confidence. Here we can see a different situation. It chose 3. That was the right answer. But you can see here, and a 0.56 for number 2, and a 0.59 for number 3. So that did way towards the number 3, but it was pretty close. You know, it was one of those things where it wasn't quite sure. It knew it was either 2 or 3, but it wasn't sure which one it was, and it went towards the number 3, which was the right answer. So you can see that sort of trends here. In this case, I had a 1.9 as my aggregate score, which means I had a very high confidence. In this case, though, I had a 0.25, which is right in the middle, because I had a relatively low confidence value here. And this kind of helps me say, okay, you know, I might want to do some, depending on this data set, I might want to do some additional training, or maybe tweak some of my configuration in my network to get that confidence up. So not only do I have a very high score in numeric accuracy, but my network is very confident that it's in the results that it's giving me. And so that's going to give me a higher confidence that it's going to be able to give me accurate results as I begin to feed new data into the network. Once I have my data set, there's a function called vxExecuteMLP, which is very simple. It simply takes the neural net array, and then whatever your input data is, for example, I use something just like this, and it makes predictions. So once I've created my network in Excel, if I want to then give this to other people, this network to other people, they don't need the full VXL 3D functions. All they need is the separate vxExecuteMLP function, which is freely distributable, and they simply need that add-in, along with just your neural net, which you've saved to a CSV file. So you can copy that into your network, like I did this with this one, and then with this, just this vxExecuteMLP function, I could then give this worksheet, I could make this worksheet available to others, and they could then use it to plug in their own data and make predictions from it. They could not retrain or train their own networks with it. They could only execute an existing network. But this would be a way that I could distribute my network, and this is the actual neural net right here. This data right here represents, in this case, this is the neural net, and I can actually come here and move this over, and so we can see what this looked like. And so very similar to the previous one, not a big surprise there, but you can see that was the network that I created, and this is what I could then build into my worksheets and make available. And I could use this for a whole variety of applications that come over here. This was a data set that we were using to test on for doing wine analysis. And again, this was another data set that's freely available that you can download. But in this particular case, it was being used to make predictions of wine quality based on certain objective measurements, lab measurements. You could take up a wine and then you could rate a quality. And then what we were doing is we were using that data to make certain predictions as far as here you can see what the numeric aggregate score was that the model predicted of the wine, how it rated the wine as being either average or above average or below average. Pretty much all of these are average, I think. And then it set a projected price point and a confidence. And this is a model that's still being trained, but you can see this is a larger data set. And I think this one, if we pull this up, and we can look at what this network looked like. And so this was a larger network. And so this is basically a wine modeling network. And so these are all of my inputs here. And these inputs all represent my lab measurements taken of the wine. And this particular data set had 4,900 white wines that were used as the sample data, and 500 wines is the test set. This had 2 hidden layers, and then my outputs, and then this gives me an aggregate score, which then, based on this model, then tells me how this particular wine, gives me a rating of how this particular wine would be as far as a quality grade, and then where I might set a projected price. And so you can see some of the applications that we have for this. And again, once this model were completely trained, I could then, this particular set has 446 connections in it, and I can make this set available, and then I could give this, for example, to a client, and they could use it to take these measurements, plug it in, and then get in a recommendation based on the model of how this wine would likely be ranked as far as its quality price point. So just some examples of how we would set this up. Hopefully this has given you a better idea of some of the capabilities of VXL 3D and what we can do as far as creating neural nets in VXL, and some of the a variety of other machine learning functions, but this is the most commonly used as the MLP function. And as we go forward, we'll be adding additional functionality to the software. Any questions, feel free to leave those in the comments section, and we'll be happy to answer them. Thank you.